So thank you guys for having me out here tonight. I've never been to Santa Fe before, so this is a fun excuse for a trip out for me. So I thought before sort of diving into tonight's subject that I would, just for fun, tell you a little bit about kind of my background and how I ended up where I am. I know some of you guys are still in school and might not know what you want to do yet, so maybe this is interesting. So I always enjoyed science, and I figured I wanted to do some kind of science, but I didn't really know what. Both my parents are software developers. They're very practical people. So when I went to college, I decided that physics sounded like fun, and there's a lot of different things that you could do with physics, so I decided to major in that. But as it happened, I went to school at Johns Hopkins, which is in Baltimore, and right across the street from my physics department was the Space Telescope Science Institute, which for those of you that are astronomy fans, you'll know is the place where they run the Hubble Space Telescope. So, from the start, right across the street, there was this whole big building packed full of astronomers doing really cool stuff. And of course, I got pulled across the street, so I started doing summer internships out there. And that was a lot of fun and convinced me to go to grad school in astronomy. So I studied astronomy in grad school and then ended up looking at extrasolar planets for my thesis work. And that's how I ended up in a planetary science department at Caltech. So I've kind of hopped across several different fields over the years, but I think hopefully give you guys a little bit of an idea tonight about some of the stuff that I worked on recently, and maybe even convince you that this is kind of a fun thing to do with science if you're interested in studying it. Okay, so if we want to study planets around nearby stars, we could imagine making a very sort of basic list of questions that we might want to answer about those planets. So the very first simplest question we might ask is, if we look at an image of the night sky, most of the points of light in that image are stars. So if we were to pick a random point of light, what is the probability that that point of light has one or more planets in orbit around it? So how common or rare are planets around other stars? Once we have some idea of how many planets are out there, we might want to then ask a slightly more detailed question, which is what kinds of planets do we find around those stars? So how common are gas giant planets like Jupiter and Saturn as compared to small rocky planets more like the Earth? So we might want to do some basic classification of our planets. If we were particularly ambitious, we might want to do even more than that. So say, for example, we found a small rocky planet that seemed like it could be kind of like the Earth. We might want to know more about it. So we might want to know, for example, if that Earth-like planet had an atmosphere. If so, what the atmosphere was made of. Maybe something about the temperature of the planet on the surface and in the atmosphere. And so all of those things would help us to figure out if the planet we found was actually like Earth, or maybe something more like Mars, or like Venus, or an entirely different kind of planet. And if we were yet more ambitious, we might even add another final sort of set of questions, which is we might want to know what the weather on our planet is like. So whether or not it has clouds, whether there are big temperature differences from one side of the planet to the other, whether or not the planet changes temperature through its orbit. So we can kind of wrap that all up into sort of weather and climate. So even though this last one sounds pretty far-fetched, right? These are planets outside of our own solar system, orbiting other stars. I'm actually going to show you today that we actually can answer all four of these questions for at least some of the planets that we're discovering around nearby stars. So this isn't a hypothetical we'd like to know. We actually are finding out for at least some planets the answers to all of these questions. And so I'm going to tell you about some of the answers that we've found as I go on. So just the first simplest question, how do we find planets around other stars? So certainly it's not a new idea that other stars might have planets like our own. Hundreds of years ago, people speculated that that might be the case, but it's only within the past about 20 years that we've actually had the ability to find planets around other stars. And the reason for that is simple, is that it turns out planets are little tiny balls of rock in orbit around a really bright star, and that makes them hard to detect. So the very first way you might think that you would look for a planet around a nearby star is take a picture of the star. So you can imagine just sort of zooming in on one of these stars and take a really, really sharp, high-resolution picture. You might be able to see the planet as a point of light next to the star. Something like this. So in theory, this is a great idea. In practice, this turns out to be a really hard thing to do. So I've cheated here. This is not a picture of a star with a planet. This is actually a picture of two stars. And the reason I cheated is that planets are much fainter and often much closer in than this star in this image. So imagine doing this, but making this point of light much, much fainter and moving it closer in. So just to give you an example of exactly how good you have to be to take a picture of a planet, there's a great analogy that Sarah Seeger, who's a professor at MIT, came up with a couple of years ago, which is if you want to take a picture of a planet next to a star, it's kind of like taking one of these big megawatt spotlights that we have out in Hollywood and putting a little firefly about a foot away from that spotlight. Now imagine you want to take a picture where you can see that firefly next to the spotlight. But imagine that you, the photographer, are not in Hollywood, you're in New York City. And that's about the scale of the problem that we have. So although it's been done for a few planets, it's a very difficult thing to do. In fact, when the National Geographic was making the cover art for this article, when they heard this analogy, they said, we're going to try it. We're not going to do it from New York, but we're going to get a spotlight, and we're going to get a firefly, and we're going to try and take a picture where you can see both. So they got everything set up, and they tried, and they could not get the picture to turn out. No matter what they did, they couldn't see the firefly next to the spotlight. Until finally they went to Professor Seeger, and they said, well, we can't get it to show up next to the spotlight, but what if we actually had the firefly go in front of the spotlight? Then it would show up. And it turns out that's exactly what we do to find planets around other stars. But for now, I'll just tell you that the firefly in this particular image was photoshopped in after the fact. So even National Geographic had to cheat a little bit. OK, but before I tell you about that, I want to tell you about a second way that we have to find planets, which is actually the way that we discovered the first planets around nearby stars about 20 years ago. And that method relies on the fact that as the planet orbits the star doesn't stay perfectly motionless. The planet actually tugs the star back and forth a little bit as it goes around in its orbit. And so if you measure the spectrum of the star, you can actually detect the Doppler shift as the star moves towards you and then away from you because of that tug from the planet. So the Doppler shift, a good analogy is if you have an ambulance that's coming towards you, you hear the sound of the ambulance actually changes pitch, gets higher as the ambulance is coming towards you, and then lower as the ambulance goes away. So same thing with light. If you have something that's emitting light and it moves towards you, the wavelength of the light goes to shorter wavelengths, so it gets blue shifted. And as the object moves away from you, the light is red shifted. So that wavelength change is something that we can measure with telescopes here on the ground. And we can actually detect that relatively tiny motion of the star due to that little planet going around it. So these are all of the planets that have been detected around nearby stars using this technique. So this plot represents about 20 years worth of work by a lot of groups, both in the US and in Europe. So just to sort of orient you on the plot, on the x-axis here, I've plotted the separation between the planet and the star. This is in what astronomers call astronomical units. So 1 astronomical unit is the distance between the Earth and the sun. So the Earth would lie right on this line here. So on the y-axis, I'm plotting the mass of the planet. And this is now in units of Jupiter masses. So Jupiter orbits at about 5 astronomical units out here. And it has a mass of 1 Jupiter mass. So it would be kind of up in this region. And Earth would be all the way down here. So this technique has found about 1,000 planets so far. And that's a lot of systems. And we can already tell that there's some interesting surprises that have come along. So one thing that was discovered very early on by these surveys is that you might notice there's a whole bunch of planets which are the size of Jupiter, but which orbit very close to their stars. So this would be inside the orbit of Mercury in our own solar system. So we call these planets, not very creatively, hot Jupiters. So we imagine that they're gas giant planets like Jupiter with much, much higher temperatures, might have some interesting effects on their atmospheres. And there's sort of an ongoing debate as to whether or not those planets formed where we see them today, or if they actually formed out where Jupiter is and then something caused them to migrate in. But either way, just the fact that these exist already tells us that many of the planetary systems that we discover will look very different than our own planetary system. So in our own planetary system, all the really big planets are relatively far out, and close in all we have is these little rocky guys. So one sort of theme that I think you'll see throughout this talk is that Whatever we thought we expected for planetary systems, extrasolar planets have consistently surprised us. So almost any configuration you can think of seems to exist somewhere out there. So planetary systems are very diverse. So I mentioned earlier Earth would be kind of down here on the plot. So that tells you that this particular technique is not yet capable of detecting Earths. It has detected a few Earth-sized planets down here, but those are all orbiting quite close to their star. So they're probably hot balls of rock without very much atmosphere. So not really a good Earth analog. Fortunately, we have a second technique that we can use to find planets. And although this other technique has found about 1,000, this technique is probably the single best way that we have to find these planets currently. So we know of more than 5,000 planets and planet candidates, most of which were detected with this technique. So I alluded to this earlier with my firefly analogy. So even though we can't see the planet, we can infer its presence from its effect on its star. The way we did that before was by measuring the motion of the stars. It was tugged back and forth by the planet. But for a fraction of these planetary systems, the planet is actually going to pass in front of the star, as seen from the Earth. So if that happens, and we were measuring the brightness of the star as a function of time, we would see when the planet goes in front of the star, it's going to block part of the star's light. So our star is going to dim slightly. And if we can measure the brightness of the star with enough precision, we can detect the very small decrease in brightness due to an Earth-sized planet going across our, for instance, sun-like star. So this technique has been a really good way to find planets. And I should mention that the reason that we have to do it by measuring the brightness of the star, you might think, well, why don't you just see the planet as a black dot going across the star? Remember, all of our stars are just points of light in our images, so we can't actually see the planet travel across the star. We can do that for our own solar system. So there's some great pictures if you just Google Venus transit. So Venus passed in front of the sun a couple years ago, and there's some really wonderful pictures online of what that looked like. And that's kind of fun to see if we only had better telescopes, what we might be able to see for these eclipsing systems. Okay, so the reason that we know of so many eclipsing systems is almost entirely due to a single telescope, and that telescope is called Kepler. So Kepler was launched in 2009, and for 4 years, it stared at a single patch of the sky located near the constellation Cygnus. So its field of view is about 100 square degrees, so there's its field of view kind of to scale with the constellation Cygnus. So it's looking sort of along the plane of our galaxy, a little bit up from that. And what it was doing is it was measuring the brightness of about 150,000 stars in that patch of sky, sampling every 30 seconds continuously for those 4 years. So it was looking for exactly that signal that I was describing earlier, a star which periodically dims in brightness due to a planet passing in front of it. And at the end of its survey, it had found about 5,000 candidate eclipsing planetary systems. So we think that almost all of those are real. The reason we say candidate is because there's a very small number of them which are probably fakes. There are other astrophysical things that can mimic the signal of a planet going in front of a star. So to be absolutely 100% sure that it's a planet for any individual system, we have to do a little bit of follow-up, and that hasn't been done for all 5,000, but we're pretty sure 90% or more of them are real planets at the end of the day. Okay, so the primary mission of Kepler ended a couple years ago. It's actually still finding new planets. It's just doing so in different parts of the sky. So now instead of staring at this one patch, it's moved on to different areas of the sky, and it stares for shorter periods of time. So if you see, you might see Kepler come up in the news, and that's because it actually is still taking data and still finding new planets today.
But its primary mission is still the same?
Its primary mission is still to find new eclipsing planetary systems, so that's unchanged, yep. Okay, so just for fun, I mentioned at the start of my talk that planetary systems are often quite different than our own. So just to give you one concrete example of that, here's a planetary system detected by Kepler, which is a planet orbiting not one, but 2 stars. So here's the system drawn to scale. So there's a hotter sun-like star and a slightly cooler, smaller star, both of which orbit very close to each other. So here's the solar system orbits to scale. There's Mercury, there's Earth's orbit. So this planet orbits both stars together, somewhere in between the orbit of Mercury and Earth, so maybe about where Venus is. So if you could stand on the surface of this planet, now we don't know that it has a solid surface, it might be a ball of gas, but if it did and you could stand on the surface, you might see something like this. So this would be a planet which would actually have 2 stars or 2 suns in the sky. So when it was first discovered, they had a bunch of articles about it in the press, and those articles made the allusion to Star Wars and said, you know, the Kepler's found the first Tatooine-like planet, for those of you that are Star Wars fans. But we think that these kinds of systems are probably pretty common, because we know about half of all the stars near the sun exist in these binary star systems. So assuming that those systems can form planets, a lot of these planets probably really do have 2 suns. So 1 sun isn't necessarily the standard planetary system. Okay, so what have we learned from Kepler, other than there are a lot of planets out there? So we can plot the relative frequency of planets as a function of their size. So I mentioned we might want to know whether gas giant planets like Jupiter are more common, or whether smaller rocky planets like the Earth are more common. So this is Kepler's answer to that question. So this is frequency of planets. So in this case, if you picked a random star, what's the probability that that star would have a planet of a given size? And here we're plotting the size in units of Earth radii. So Jupiter would be out here on the right. So about 1% of the stars that Kepler looked at had a Jupiter, which, and these are all planets that are orbiting relatively close in. So about 1% had a hot Jupiter. About 6% have a Neptune-sized planet. Neptune would be right here in the middle. And then you see there's a big rise in the frequency of planets. So Kepler tells us that although planets in general are common, small planets are much more common than large ones. Now that's reassuring for those of you that might want to know what the prospects are for life elsewhere in the universe. Kepler tells us that there should be a lot of Earth-sized planets out there. Interestingly, the peak of this plot isn't at 1 Earth radius. The peak of this plot is actually for planets a little bit bigger than the Earth. Now remember, I said Neptune is here and Earth is here. In the solar system, we have nothing in between those 2 planets. So in the solar system, there is no planet with a radius that's 2 to 3 times that of the Earth. So one other big surprise to come out of Kepler was the discovery that there was a whole new class of planets which had no solar system analog. We call those planets super-Earths because they're bigger than the Earth, but the truth is we have no idea what kind of planet it actually is. So they may be scaled-up versions of the Earth that are mostly rock, but they may also be kind of mini Neptunes, just take Neptune and shrink it down in size. Or they might be an entirely new kind of planet. So you can imagine making one, for instance, that has a very large amount of water in the mantle. So we would call that a water world. So one of the primary goals of the Kepler mission was to estimate the fraction of stars that had Earth-sized planets located in what we call the habitable zone around the star. So that refers to the region where you're far enough away from the star that if you were in Earth, you wouldn't roast, but you're still close enough to the star that you could have liquid water on the surface. So in the solar system, the habitable zone would be outside the orbit of Venus, and it would stop somewhere just maybe around the orbit of Mars, maybe a little bit inside that. So we sit in the middle of the habitable zone for the sun. So you can ask, of all these systems, how many of these planets are inside the habitable zone of their star, and in particular, how many small planets there are. And so Kepler tells us that something like 5 to 10% of sun-like stars have a small planet, which could be rocky, located at the right distance that it might have liquid water on the surface. There are lots of caveats there because we don't actually know. So all Kepler tells us is the radius of the planet, because all we know is how much light the planet blocks when it goes in front of the star. So Kepler alone doesn't tell us whether or not our 1 Earth radius planet actually is like the Earth. But we can ask at least how many small planets there are in the right spot. Okay. So, yes. Sure. Yeah.
So if the histogram is just for planets with periods of 500 days, does that affect the distribution in the sense that like our solar system only has what, 1 planet that
Yes.
happens to be the smallest? So is that
Yeah. So that's a great question. Right. So I kind of glossed over the fact that this plot is only for planets with orbital periods less than 100 days. So that would be planets sort of about the orbit of Mercury and inside in our own solar system. So the reason for that is that this technique relies on the fact that the planet has to go in front of the star. So if you think about the orbits of the planets being randomly oriented on the sky, the probability that the planet will pass in front of the star varies with its distance from the star. So if you're very close to the star, you could have a wider range of orientations and you'd still get an eclipse. But as you move the planet further away, there's a smaller and smaller range of orientations where you see that eclipse. So this technique is really good at finding close-in planets, and it's much less effective at finding planets further out. So it found just a handful of planets with a 1 year or longer orbital period, and I don't think it found any as far out as Jupiter. So if we added the solar system to this plot, Earth wouldn't be on this plot, because Earth would be outside this region that Kepler considered, and Mercury would be too small to go on this plot. So adding the solar system to this plot wouldn't change anything at all.
No, I understand.
Yeah.
Is this distribution the real distribution in the galaxy, or how did
Yes.
Is it overpopulating the smaller sizes because of your selection?
Yes. So if we could complete our survey and go out all the way out to beyond Neptune's orbit in our own solar system, we might see that there would be more large planets. So that's certainly a question that we would like to know, and which we don't yet have data to answer. I don't think that you're going to get something that's flat all the way across. So I don't think that there's a factor of 10 of these guys lurking in the outer part. The radial velocity survey gives us some idea of how many of them might be out there further out. So they would come up a bit, but maybe by a factor of a few, not by a factor of 10. Yeah. Okay. So we can learn something about what kind of planet we found if we put these two techniques together. So I mentioned before we can infer the presence of a planet because it perturbs the star, so we see the motion of the star. So the size of that motion tells us the mass of the planet that's doing the perturbing. Big planets are going to yank the star around more. Small planets are going to yank the star around less. So the amplitude of this signal tells us the mass of the planet. At the same time, if the planet goes in front of the star, remember not all of these do, but some of them do, and we can measure the eclipse, we can measure the amount of light blocked by the planet, and that tells us the radius of the planet relative to the radius of the star. So if we have a mass and a radius, we can calculate a density for the planet. So that is what allows us to do our initial classification. So we know that some planets have very low densities. So Jupiter is made mostly of hydrogen and helium. Those are very light elements. Gas that's mostly hydrogen and helium is very puffy. So planets made from primarily gas tend to be very low density, whereas planets that are made mostly from rock, like the Earth, would have much higher densities. So with a mass and a radius, we can distinguish between rocky planets and puffy gas-dominated planets. So we can do that by putting the planets on a plot. So this is just showing you a little bit more carefully what I was saying in words. So if we plot the mass of the planet on the y-axis, so this is now in units of the Earth mass, and the radius of the planet in units of Earth radii on the y-axis. Just for comparison, I've shown you the solar system planets. So here's Jupiter, Saturn, Uranus, and Neptune, and here's the Earth and Venus all the way down here. And I'm overplotting, so these black points are all of the known extrasolar planets where we have both kinds of measurements. And I'm comparing those to theoretical models that tell me if I make a planet entirely, for instance, of hydrogen, at a given mass, what radius would I expect to see? So the hydrogen planet is here in light blue. We could also imagine making a planet entirely of water here. So at the same mass, a water planet would be a bit more compact than a hydrogen planet. If we made our planet entirely of rock at that same mass, the planet would have an even smaller radius. So here's our rock line. And if we made our planet entirely of iron, it would be down here along this line. So in order to figure out very roughly what kind of planet we have, we just have to look and see what line it falls closest to. So planets which are the mass of Jupiter mostly lie near this hydrogen line. So that tells us that big planets, like Jupiter, seem to be made mostly of hydrogen and helium. As we move down and to the left, you see that planets like Uranus and Neptune fall a bit below this line. So that's because these planets have a large rock or ice core surrounded by a mantle of hydrogen and helium. So those planets are made of a mix of a couple different things. moving even further down towards the Earth. So Earth and Venus, you can see, lie basically on the rock line. So even though Earth and Venus have atmospheres, that doesn't change their radius very much. So they're, in this plot, they're basically balls of rock as far as we can tell. And you can see that, sure enough, some of the planets that we found are also dense enough that they are probably mostly rock, but many of them are less dense than that. So there might even be some of these water worlds I was mentioning earlier. And there are probably planets that still have a lot of hydrogen and helium, even though they're not made entirely of that. And just to sort of remind you, remember there's this whole new category of planets called super-Earths, which I said were bigger than the Earth but smaller than Neptune. So I said before we didn't know what kind of planets those were. So we didn't know if they really were rocky planets like the Earth or sort of scaled down versions of Neptune. So this plot is our first chance to answer that question. Is a super-Earth really a ball of rock? Or does it look sort of like a smaller Neptune? And it looks like the answer is that they're kind of a mix. So you can see that in this mass range, some of them are rocky, but many of them are up here where they must have a lot of water or maybe even some hydrogen and helium on top. So this probably isn't one single kind of planet. This is probably a mix of a bunch of different kinds of planets. So one other thing that I kind of touched on earlier is that these surveys for eclipsing planets, most of the planets that they find are very close to their star. So the histogram that I showed you before said most of the planets found by Kepler have orbits inside the orbit of Mercury. There are systems detected by Kepler which have not one but multiple super-Earths all within this very close-in region. So if we compare, again, sort of these systems to our own solar system, this is sort of one extreme example. So this is a system which has 5 of these super-Earths all inside the orbit of Mercury in our own solar system. And that's really kind of interesting because that's a very empty region in our solar system. So something was different here, and we're not quite sure what that something was. So there are 2 theories. One is that these systems had more material to form planets very close to the star. So these planets formed where we see them today. But there's sort of a competing theory, which is that these planets may have formed farther away from the star, where we see bigger planets in our own solar system, and something caused them to migrate in, maybe interactions with the gas disk, maybe interactions with other planets. And we don't actually know which of those is the case for these systems. So if we wanted to answer the question, these super-Earths are everywhere, why doesn't the solar system have one? The answer to that question will be different depending on how we think these planets form. So we might be able to test that if we could measure the compositions of these planets. So if the super-Earths formed far away from the star, we think that these small planets probably form mostly by accreting things that are solid in their region of the disk. So if they form far enough away from the star, there's going to be a lot of water ice that they could sweep up, and they should have a lot of water in their envelopes. On the other hand, if they form very close to the star, the gas is very hot, water is in gas phase, so the only solid materials that they could accrete close to the star would be rock and metal. So the composition of the planets should help us figure out where they formed relative to the star. Okay, that's great. I just told you how we could do that. We measure a mass, we measure a radius, we put it on the plot. If the density is high, we say it must have formed in place. If the density is low, we say that it probably has a lot of water and it formed far out. Problem solved. So there's a catch, and that catch is the fact that these planets can have atmospheres. So I said for the Earth, throwing an atmosphere on top of the ball of rock doesn't change the radius very much. And that's because Earth has a very thin atmosphere compared to the size of the planet. But that isn't necessarily true of all of these planets. So you could imagine making a planet which was, by mass, mostly a ball of rock, but adding an atmosphere of hydrogen and helium on top. Now remember I said those are really puffy gases, so you don't have to add very much to change the radius of the planet by a lot. And in fact, you could imagine constructing 2 imaginary planets, both of which have exactly the same mass and radius, but which have entirely different compositions. So here on the left, you could make a planet which has a small rocky core surrounded by a mantle of water, but you could make exactly the same mass and radius for your planet by having a slightly bigger rocky core surrounded by hydrogen and helium gas. So if all you have is a mass and radius, you can't tell the difference between these 2 scenarios. Darn. Okay, so obviously we need to learn something else about the planets. Well, if we could measure the atmosphere of the planet, that would be a great way to tell the difference. This planet should have a steam atmosphere. It's a water-dominated planet close to the star. Water gets warm, it turns into steam, so it should have an outer layer of steam. This planet has a hydrogen and helium atmosphere. So if we measured its atmospheric composition, it would look very different than that one. So if we could just add one more piece of information to our list, we might be able to get ourselves out of this dilemma. Okay. So how do we actually measure the composition of the atmosphere of a planet that we can't actually see orbiting a distant star? So it turns out that the answer lies in the geometry. So in particular, these eclipsing systems turn out to give us a lot more information than just the radius of the planet. So I mentioned before, when the planet goes in front of the star, it blocks part of the star's light. And by measuring how much light it blocks, we can determine the radius of the planet. But what I didn't mention is if that planet has an atmosphere, the atmosphere will be opaque at some wavelengths and transparent at other wavelengths. So if you're looking at a wavelength where the atmosphere is clear, you can see through it, then the planet's going to block less of the star's light. But if you look at a different wavelength where the atmosphere is opaque, then the planet's going to look bigger and it's going to block more of the star's light. So the amount of light blocked by the planet should actually vary as a function of wavelength if the planet has an atmosphere. And that wavelength dependence will actually tell you the different gases that are present in the planet's atmosphere. If we wait about half an orbit, these planets will actually pass behind their star. And if we look at infrared lights, these planets turn out to be a little bit brighter. The star gets a little bit fainter, and we can actually detect the small decrease in light when the planet goes behind the star, disappears, and reappears. And so I'll tell you more in a minute about how that measurement will actually let us take a temperature for the planet. But it also tells us, if we do it in different wavelengths, about the composition as well. Lastly, we can actually make maps of these planets. So I'll tell you at the very end of my talk about if we measure the changes in the brightness of the planet as it goes around, how that actually tells us about the properties of the day side of the planet and how they differ from the night side. But for now, let me just say that there's a lot of tools that we have that can help sort of fill in our picture of these planets. So I'm going to start with the one that answers the question that I posed before, which is what is the composition of the atmospheres of these planets? But before I actually show you the observations, I want to tell you a little bit about where the data comes from. So we make these observations using a couple of different telescopes. Many of the observations are made from space. So the Hubble Space Telescope has been sort of one of the main telescopes that we've used to do a lot of these studies. It's a wonderful telescope. We also use the Spitzer Space Telescope, which observes at slightly longer infrared wavelengths. And some of these observations we also make from the ground. So being at Caltech, I have access to the Keck Observatory, which is on the summit of Mauna Kea. So this is a pair of 10-meter telescopes. And we can also use those telescopes to make some of these same observations. So there are some, these are about 14,000 feet. Yep. So there are some pluses and minuses to using each of these telescopes. So the plus side of using space telescopes is that you get absolutely wonderful data. You know exactly what you're going to get. You get beautiful measurements every time. And so some of our most precise, most sensitive measurements have come from Hubble. But there's a trade-off, which is that when I get data from the Hubble telescope, the way it works is I write a proposal. I say I want to use the Hubble, I want to point it at this star and make this measurement. And then I wait 3 or 4 months, and I hear back, and they say the committee has reviewed your proposal and decided to give you time on the telescope. I say, great, OK. Then I go to my computer and I write a script. And that script tells the telescope what it needs to do. Point at this star, look at this wavelength, take this many images for this amount of time, send the data back down. So I send that script off to the telescope, and then I wait. It goes into the scheduling queue. I wait some more. Maybe 6 months later, I get an email that says, the Hubble telescope has taken your observations. You can get the data from the online archive. So then I go to my computer, and I log into the online archive, and I get the data. So unfortunately, I don't actually get to go to the telescope to do my observations. So all of this is done from my desk in my office on my computer. And that's one reason why I really like to use telescopes like Keck, is that one of the really fun things about being an astronomer is the opportunity to actually drive up a mountain to go to an actual telescope, stay up all night, and be able to walk out of the dome in the middle of the night, look up at the sky and say, that's the thing we're looking at tonight. So it's a lot more fun when you can actually visit the telescope. So it's particularly nice because the Keck telescope is located in Hawaii. It's great to have an excuse to go to Hawaii. It's beautiful at night up there. It's a fun thing to do. They're impressive telescopes. And then, there's the beach. But you might notice this picture. I'll tell you, this picture was taken in May, one time when I made a trip up. And you'll notice that there is snow in this picture. So when I go observing on Keck, even during the summer, I pack my winter parka, I pack my hat and my gloves, and I trudge through the snow to the telescope. So unless I drive all the way down the mountain to go to the beach, it's a pretty cold experience, even observing from Hawaii. But it's still fun to do. OK, so once we've collected our data, what do we actually learn about these planets? So here's an example of an observation where we were looking at a Neptune-sized planet. It orbits, it's again one of these guys that orbit relatively close to their stars, so I'll call it a warm Neptune. And we wanted to measure the composition of this planet's atmosphere. So we pointed Hubble at it, and we measured how much light the planet blocked as a function of wavelength. So in this case, we were looking at infrared wavelengths. And so here is wavelength on the x-axis, and then I'm showing you how much light the planet blocks on the y-axis. So at wavelengths where the planet is opaque, or where the atmosphere is opaque, the planet appears larger, and it blocks more of the star's light, so that would be up on this plot. At wavelengths where the atmosphere is clear, the planet blocks less light, so that would be down on this plot. So we're looking for a change in the apparent size of the planet as a function of wavelength, and that'll tell us about the gases that are present in the Neptune-like planet's atmosphere. So in black is our data, and I'm comparing that data to a couple of different models. So the very first thing that you probably notice is, hey, that data is flat. That measurement looks like the radius is exactly the same across the whole range of wavelength that you looked at. So what is the signal that you were trying to measure? You said there was going to be a change. So in red is what we expected to see when we made these observations. So this was our model at the start. This is a planet which is the size of Neptune. It also has a radius, so mass and radius are both similar to Neptune. So based on what I told you earlier, that means that it should have a rock or ice core surrounded by a mantle of hydrogen and helium. So when we model its atmosphere, we expect it to have a pretty puffy atmosphere, which would give us these nice large variations as a function of wavelength. And in this case, this particular feature would be due to water vapor mixed with the hydrogen and helium in the planet's atmosphere. So we were looking for water absorption. So we didn't see that. Instead, we saw something that looked flat as a function of wavelength. So there's two possible explanations. One is that the planet doesn't actually have a hydrogen-rich atmosphere. So if you take all the hydrogen out of the atmosphere, you can kind of shrink down the width of this little blue ring that's doing the absorbing. So that's the blue model here. So this is just for fun saying, what if the planet had a pure water atmosphere? We don't think that that's actually the case, because the density is so low it has to have hydrogen and helium. But OK, that would work. But it turns out there's another scenario that we didn't consider before we took the data, which is that the planet might actually be cloudy. So if you take your Neptune and you imagine making clouds high up in the atmosphere, just like on the Earth, clouds are going to block the ability of the starlight to pass through. So clouds are going to mask the signal that we expected to see. So even though we're observing from space, we don't normally worry about weather. It seems like in this case, we were foiled by bad weather, not on the Earth, but on the planet we were trying to observe. OK, so what might these clouds be made of? So this is a Neptune-like planet, which probably has clouds. It's close enough to its star that it's much warmer than our Neptune. And so we can try and figure out what kinds of clouds it might have in its atmosphere. So one theory is that you have some gas which is present in the atmosphere. And when you get to the top, the atmosphere is cold enough and thin enough that whatever that gas is, it's condensed into a cloud layer. So the analogy would be water clouds on Earth work this way. But this planet is much too hot to have water clouds. So if it had clouds, those clouds would have to be something that condensed at a much higher temperature. And it turns out that two plausible things that might condense at high temperatures are zinc sulfide or potassium chloride. So this planet might actually have salt clouds, which is kind of fun to think about. It might also have something a little bit different, which is we see in our solar system that Titan, which is a moon of Saturn, has a hazy layer in its atmosphere, which is due to photochemistry. So ultraviolet light from the sun hits the atmosphere of the moon. There's methane present in the atmosphere, so it breaks apart the methane molecules, and then they reform as these long hydrocarbon chains, which create this sort of haze. So we call this, not very creatively, this sort of a photochemical haze. So that might also be another explanation for the clouds that we see on this planet. So even though we were clouded out for our observations of this Neptune, I kind of started this whole thing by saying we want to use this technique to figure out what the atmospheres of super-Earths are made of, because we see there's a bunch of super-Earths that might be water worlds, or they might be balls of rock with hydrogen and helium, and we don't know which it is. So we've used this technique to observe 2 super-Earths to date. There are not very many of them that we can observe with Hubble, because they're very small planets, so we need to pick sort of the closest systems, but we've looked at 2. And unfortunately, both of them look exactly like the Neptune that I just showed you. So both of them, the radius of the planet is the same across all the wavelengths that we observe. So it seems like super-Earths, like our Neptune, might have these cloud layers which are preventing us from measuring the composition of their atmospheres. So we hope that our luck will be better, and that if we look at a 3rd or a 4th super-Earth, that we might eventually find one without these clouds. But for now, I can't actually give you an answer to that question, because it seems like these cloud layers are pretty common. Okay. So taking a step back from super-Earths, I want to give you some examples of some other observations that we've made that tell us more about the properties of these planets. And so for the very end part of my talk, I'm going to tell you primarily about bigger planets, because those are easier to study. So in particular, I'm going to show you some observations that we've made for hot Jupiters. So these are these Jupiter-sized planets that orbit very close to their star. And we like hot Jupiters because they allow us to test all these techniques. They give us the biggest possible signal. And so whenever we test a new technique, we want to do the easy thing first and then move on to the hard thing. So for us, super-Earth's the hard thing, hot Jupiters are the easy thing. So hot Jupiters are the best examples that I can show you. All right, so what happens when we look at a hot Jupiter when it goes behind the star? So I mentioned before, this is how we can actually take the temperature of the planet. And just to sort of show you what I mean, here's an image of a person which was taken in infrared light. And you can see that the person's skin is brighter, and where their clothes are, it appears fainter. And that's because at infrared light, the brightness is related to the temperature. So a person's skin is hotter and their clothes are cooler. So if we can measure the brightness of the planet in infrared light, we can assign a temperature to the planet based on that infrared brightness. So that's exactly what we do. So here's just what the actual, so this is brightness of the star as a function of time. So here you see the light from the star and the planet together. Here the planet has disappeared behind the star, and here it comes back out again. And these particular observations were taken, I think, at 8 microns. So this is easily into the infrared. So this is definitely thermal emission from the planet. And in this particular case, this hot Jupiter turns out to have a temperature of about 1200 Kelvin based on its brightness at that wavelength. We don't have to make these observations in the infrared. It turns out, although it's much harder, yeah, 1200 Kelvin, almost hot enough to melt rock. Yeah, very hot. So if we were to make the same kind of observation in visible light, we would actually detect something different. So in infrared light, you're seeing the thermal emission from the planet. In visible light, you're seeing mostly light from the star that's reflected off the planet's atmosphere. But it's kind of fun to think about, because if we could actually visit one of these planets, we see invisible light. So if we wanted to know what color a hot Jupiter would be, we would need to know how much light it reflects across the visible spectrum. And so someone has actually gone and made this measurement with the Hubble telescope for one of the hot Jupiters that we've been observing. And so it turns out when you observe with Hubble, so again, looking as the planet goes behind the star, disappears, and then reappears, it turns out that this particular hot Jupiter reflects more blue light and less red light. So even though this is sort of the artist's impression that we use to illustrate these hot Jupiters, it turns out if you could send a spacecraft there and actually view them, they would be blue to the human eye. They'd be blue and they'd be kind of dim. They're not very bright, not very reflective, generally speaking, but even though they're dim, they would definitely be more blue than red. So one fun fact about this hot Jupiter is that it also has clouds in its atmosphere. It's a bit bigger and a bit hotter than the Neptune I showed you before. So we think that the clouds in this atmosphere are probably liquid rock clouds, or so silicate kind of glass type things. And if you think about that, that almost makes sense, because this planet is blue. And if you can imagine clouds of liquid glass, you might think that those clouds would look blue. So it's not we don't know for sure that that's what the clouds are made of, but it makes a nice kind of story, and it's certainly very plausible that this blue color is because of the presence of these liquid rock clouds in the planet's atmosphere. So kind of fun to think about. Okay, so one other thing that we like to do is we like to make, when we can, maps of these planets. So we want to measure the brightness of the planet as it goes around the star. So why do we care about maps? Well, I mean, maps are fun, for one thing, but another, a lot of these planets orbit very close to their star. So when you have a planet that orbits close to the star, what's going to happen is the spin of the planet is going to synchronize with its orbit over time. So we think that almost all of these planets are what we call tidally locked. So that means they have a permanent day side and a permanent night side. Now, we can point to an example in our own solar system. So the moon is actually tidally locked to the Earth. So that's why we always see the same face of the moon. So similarly, these planets always show the same face to their star. Kind of an interesting fact, but it could have big consequences for the planet. So imagine that you have a planet where one side it's always day and another side it's always night. That's going to have some pretty extreme effects on the properties of the planet. You might have a day side that's really hot and a night side that's relatively cold. Or maybe if you're lucky and you have enough atmosphere, maybe you just get really strong winds that carry that hot gas from the day side around to the night side. So we would like to know, for these close-in planets, whether or not they have large day-night temperature differences, or if winds are pretty good at mixing things around in their atmosphere. And we can actually answer that question by making maps of the atmosphere, in particular making maps of the temperature on the day side and the night side. So the way that we do that is by looking in infrared light. So remember, in infrared wavelengths, brightness is related to temperature. And we measure the change in the brightness of the planet as it goes around the star. So this is an observation of a hot Jupiter, which goes for about half of the planet's orbit. So here at the start, it begins when the planet goes in front of the star. So that's this first dip that you see. And this is an observation made with the Spitzer Space Telescope at about 8 microns. So here the planet is passed in front of the star. So if you think about what side of the planet you're seeing at that point in time, you're seeing the night side of the planet. Now, as you wait, that planet's orbiting around the star until eventually it's come halfway around, and here is where it disappears behind the star. So this is the secondary eclipse. So you've gone from seeing the night side of the planet, and you've watched, in effect, the day side rotate into view. So when it goes behind the star, you're seeing the day side of the planet facing towards you. So if this hot Jupiter had a really hot day side and a really cold night side, then we should see the planet increase in brightness as that day side comes around into view. So what we're looking at here is not this eclipse, not that eclipse, but what we're interested in is the stuff in between. So how is the brightness of the planet changing as we see different phases for the planet? So in order to answer that question, we need to change our scale on this plot. So it's pretty hard to see what's going on here. It looks pretty flat, but if we just make the same plot, but now blow up the y-axis, so this is just changing the scale on the y-axis. Here's our transit. Now it would go all the way down off the bottom of the plot. Here's our secondary eclipse. Now you can see it looks much deeper, but now we can really see what's going on in between. And sure enough, you can see that the planet did get brighter in infrared light as the day side rotated around into view. So that tells us, not surprisingly, that the day side is hotter than the night side. We probably could have predicted that in advance, but what we'd really like to know is how much hotter the day side is and how much colder the night side is. So again, we can take this brightness and we can assign it a temperature. So in this case, the night side would be about 1,000 Kelvin, and the day side would be about 1,200 Kelvin. And I'll translate that into Fahrenheit in just a minute. But those are both really high temperatures. This planet is the one that we thought might have liquid rock clouds in the atmosphere. But at the same time, that's not that big of a difference compared to what it might have had. So this actually tells us that this particular Jupiter has very fast, strong winds in the atmosphere that are pretty good at keeping the night side warm, even though the night side never gets any direct light from the star. So what I've just described here is sort of a cartoon picture of the planet, where you've got a day side and it has one temperature, and you have a night side and it has another temperature. But the slope here actually tells us something more, gives us more detail than that. So we can take this curve and we can invert it to make a map of the temperature of the planet as a function of longitude. So this is the map that we get from these observations. So here at the center of the map is the substellar point. So this would be sort of high noon on the planet. This would be the middle of the day side. And then here are the same temperatures I was giving you before, but now in Fahrenheit instead of Kelvin, just for comparison. So the night side would be here on sort of the two edges. So this would be midnight on the planet. And interestingly, you can see that the hottest part of the planet is actually not at high noon. The hottest part of the planet is shifted a little bit over. And we think that there's a simple explanation for that, which is that, as I mentioned before, we think this planet must have relatively strong winds. So imagine a belt of wind blowing from left to right on this plot. That wind is going to take the hot gas here, and it's going to carry it a little ways downwind. So the size of this shift actually tells us something about the wind speed in the atmosphere. And that wind speed that we infer matches up pretty well to the wind speed we think we need in order to keep the night side this warm. So there's a good kind of self-consistent picture that we can paint here. Okay, so having talked about hot Jupiters and some about super-Earths, at the very end of my talk, I wanted to just briefly tell you guys a little bit about sort of where things are going. So in particular, we're studying relatively large planets right now, but we'd really like to characterize Earth-like planets. So we'd like to not just be able to find them, but also to measure their atmospheric compositions, to figure out what temperatures they have, maybe even to learn something about the climate on the planet. But there's a big challenge, which is that the size of the signal that we measure scales with the area of the planet. So this is Jupiter and Earth to scale, and you can see that the Earth is much, much smaller than Jupiter. So if you want to take this same idea, apply these same techniques to studying Earth-like planets, you're trying to measure a signal which is a factor of 100 or more smaller than what we've measured so far. So that's pretty tough to do. And in particular, we can't just take the same old telescope. Hubble's a great telescope, but it's only so big. We can't take Hubble and point it at one of these small planets and all of a sudden measure a signal that's 100 times smaller. So right now, this signal is beyond what we can measure with telescopes that are currently available. But there might be a solution. So astronomers are clever people. And you might say, well, if it's beyond the current telescopes that we have, we just need to build a really big telescope in space. And we would love to do that, but really big telescopes in space are really expensive. And even the next one that's planned for launch, which is the James Webb Space Telescope, that's going to go up in 2018, is not going to be big enough to measure the signal of an Earth going across a sun-like star, or at least not to detect the signature of that Earth's atmosphere. So even our next big telescope coming up can't study the atmospheres of Earth. It's just not big enough. But if we're willing to relax our requirements a little bit and instead consider an Earth which orbits a much smaller, cooler star, then we might be able to redeem ourselves a little bit, because the signals that we measure scale as the size of the planet relative to the size of the star. So if we want to study really small planets, one sneaky way to do that is to look for small planets around small stars. And if we could just find more systems like that, we can get, for instance, in this case, about an order of magnitude back in the signal that we're trying to measure. So we can make the problem a little bit easier for ourselves by just choosing wisely the kinds of systems that we'd like to observe. So those planets are interesting to think about because they're not going to be exactly like the Earth. So even if you took the Earth, same atmosphere, same interior, if you put it around one of these small, cool stars, it's going to change things a little bit. So for one thing, you'd have to put that Earth much closer to the star in order to keep it at the same temperature. These stars are dimmer, they're fainter. So if you want to have a nice kind of temperate Earth with water, you have to be a little closer in. These stars also emit much more red light and less blue light. So the sky on one of these planets would have kind of a reddish tint to it. That might have consequences for life on Earth. Plants convert sunlight into energy, and that's a wavelength-dependent process. So if you have a star that has a different, is brightest at a different wavelength, you might need slightly different kind of equivalents to photochemistry for your plants. And just for fun, you might notice this particular artist's impression actually has two stars in the sky. So again, going back to what I mentioned at the beginning, you might also imagine that you could have maybe Earth-like planets with two stars, and that would also affect the planet. Okay, so going back to the set of questions that I made at the start, just kind of making sure that I've actually answered everything here. So let's think about what I asked at the start. So I started by asking how many planets are out there. So if we pick a random star in the sky, what's the probability that that star had a planet? And I used the results from the Kepler survey to tell you that planets are quite common. So the odds are pretty good. If you pick any random star, it's going to have at least one, maybe more planets. And that small planets are much bigger, much more common than large planets. I asked what kinds of planets we find in these surveys, and I showed you how by combining these two techniques, the eclipses and the Doppler measurement, that you can measure density for the planet, so you can tell the difference between one that's mostly hydrogen and helium and one that's mostly rock. And we think that small planets are common. We think a lot of those small planets may be rocky. Large planets somewhat less common, and the large planets seem to be almost all made of hydrogen and helium. So there seems to be a correlation between the size of the planet and its composition. Okay, reasonable. We talked about how you might characterize the planet in more detail, so how you might determine if it has an atmosphere, what the atmosphere is made of, maybe even take a temperature for the planet. And lastly, we talked about how common Earth-like planets might be, and whether or not you might be able to determine whether or not that small planet that you found actually was Earth-like, if it had an Earth-like atmosphere, if it was at the right temperature to have liquid water, using some of these techniques. So I always like to finish with this image, because the one thing that I haven't told you about, I've talked about a lot of different planets, but I haven't actually shown you where any of those planets are located in the galaxy. So this is just an artist's impression of our own galaxy. So there's the center, here's the sun, partway out, located in one of the spiral arms. So I can just draw a little kind of white circle that encompasses all of the planets found by these two survey techniques, the Doppler technique and the eclipse technique. So if I draw that circle on this plot, it actually looks a little bit more like a lollipop, because the Kepler survey looked a little farther out in that direction. It's tiny. So all of the planets that I told you about today are in the local neighborhood of the sun. So we haven't even begun to find planets on the other side of our own galaxy. So that gives you some idea of kind of how far out we've gone and just how many planets there are out there still, which we have not yet detected. So this is really sort of just scratching the surface of what's out there. So as many surprises as there have been to date, I suspect there are a lot more still waiting out there in the galaxy. So with that, I'll stop and take questions.